Hey there, I'm Ken the Metal Professor, and I'm here to solve 3 problems related to arc length. I was working with somebody the other night, and we got into a conversation about arc length and doing some example problems, and so I thought I would repeat those problems here so they can be seen by lots of people, I guess. Check my viewer count. Lots of people. Okay. Anyway, so what I'm going to show you here is a little bit of web work. You may or may not be used to it or have seen it before. But, MyMathLab, WebAssign, those are a couple of examples of proprietary math homework systems. WebWork is open source, so it can be used by anyone. And this is actually my own implementation of it that I was able to get running by following their instructions. You just need access to a server, so I'm using Amazon Web Service for this. It's not quite locked down, but it's useful. So I'm going to show the 3 problems where we're asked to calculate the arc length of a curve, work through them, and then check that those answers are indicated as correct. Now, the thing about arc length problems is that the integrals can become very, very nasty very quick. So whether or not your instructor is somewhat lenient on the use of technology for solving integrals, this may or may not be an excruciatingly awful subject or not. The setting up of the integrals isn't so bad, but the functions that you're working with have to be selected pretty carefully to generate a resulting integral that can be evaluated reasonably by hand. So maybe one of these can be done by hand, but the other 2 we're going to use a little bit of tech help to get the job done. Okay, so the first question at hand in this review of arc length is to find the arc length of the curve y equals natural log of cosine of x from x equals 0 to x equals pi over 4. So here is that problem stated again, so we can start working. Now remember that the goal of this is to compute the arc length, and that is given by the integral from your starting value of x, in this case, to your ending value of this nasty integrand Isn't that great? This is why these integrals don't end up coming out to something manageable unless the functions are selected very carefully. But anyway, to generate this integral, we have to take the curve of interest, find the derivative of the function describing the curve, square it, add 1, slap it under a square root, and then put it in an integral. I know it's enticing to just put that expression down as its big, gigantic, enormous self and start filling in details. What I will suggest is to build it from the ground up, right? You don't even worry about looking at the square root or even the integral sign until you've seen what that core section looks like, because it's better to concentrate on the simplification of that core guts of that square root. So I'm just going to build it up one step at a time. So step 1 is I'm just going to calculate dy dx. So up here we have the natural log of something, and if you're good at the chain rule, you know that the derivative of the natural log of something is 1 over that thing times the derivative of that thing. The derivative of cosine is negative sine, and you may remember that sine over cosine is tangent, so this becomes a negative whoops, I jumped the gun. It'll become a negative tangent of x. Okay, now the square of that for this term is tangent squared, and then we're going to add 1 to it. So I'm going to go ahead and build that all at once. So 1 plus the square of the derivative is 1 plus tangent squared, and if you're good at your trigonometric identities, you might recognize that as secant squared. And when I'm done with this problem, I'll show you a little trick about how you can, it's not a trick, it's a quick way to do a derivation of an identity to see if you have the right one in mind or not. Okay, so back up to here again. We've now computed the inside of that square root. And so now we can do the square root of this thing here. I'll be lazy and put that in there. Don't do that on your homework though. Write it out completely. We're looking at the square root of secant squared. And because the secant is going to be positive everywhere in the interval of interest from 0 to pi over 4, we don't have any sort of plus minus nonsense to worry about this, and the square root of secant squared is just secant of x. And so, altogether now, the arc length of this stretch of curve is going to be the integral from the starting value to the ending value of interest, 0 to pi over 4. The square root of, etc., turned out to be just secant of x dx. Okay, now this integral looks harmless, right? However, it is brutal to try to do it by hand. There is no quick and easy antiderivative of secant of x like there might be for cosine. So go look up somewhere how to do this integral by hand. It involves a trick of taking the secant and multiplying it up and down by secant x plus tangent x so that you can multiply through and prepare yourself for a u substitution. It's bloody awful. Okay, so this is a case where perhaps a little bit of numerical help can be useful. So I'm going to presume it's okay to do this. I'm using Maple. You can type this into Wolfram Alpha if you would like, or anything else you happen to have handy. But here we go, integral from 0 to pi over 4 of secant of x, and we get the natural log of 1 plus the square root of 2. So that should be the final value for that integral. And now I'm going to go back here and try it and type in natural log of 1 plus square root of 2 for my answer, check my answer, and ta-da, we get the WebWork green, which gives you that feeling of peace and calm. If you've used WebWork before, you know that red, but green, nice and peaceful. Okay, so that was a successful problem. Now I'm going to hit the reset button. Arc length problem number 2. Find the arc length of the curve x equals 7y to the 3 halves from y equals 0 to y equals 3. Now this sounds a little bit backwards because usually it's y equals f of x between x equals this to x equals that, but this flips the script on that and it doesn't matter. The goal for this is to construct an arc length. Here I'm writing and you can't even see it yet. The goal is to construct and solve an integral which is going to be exactly the same thing as before, except instead of dy dx, it'll be dx over dy. And we're going to integrate with respect to y, meaning we need to know the starting and stopping y values for this function. But we do. Okay, we have a function of y, 7y to the 3 halves, from y equals 0 to y equals 3. Okay, so I have x equals 7y to the 3 halves as the function we're going to mess with. And again, I'm not going to build the integral and then fill in the details. I'm going to build the details and then construct the integral. So I just want to see dx dy. Well, that's not bad. That's 7 times 3 halves y to the 1 half, or 21 halves y to the 1 half. Now we're going to square that. Now, hopefully you can see that squaring this is not bad. We're going to generate a large number, 21 squared, but the square of y to the 1 half is just going to be y, right? So not so bad. So I'm going to go ahead and build 1 plus dx dy squared all together. That's going to be 1 plus 21 squared over 4 times y. Now, what the heck is 21 squared? Well, let's see. 440 something. 441. And there I go writing where you can't see it yet. Okay, so that function simplifies to 1 plus 441 over 4 times y. 441 is not divisible by 4, so we can't simplify that value anymore. Okay, and so I'm going to flip the page here. The arc length we want, remember we're going from 0 to 3, and now we have the square root of this quantity that we just created. So I've got the square root of 1 plus 441y over 4 dy. Now, this integral is doable by hand. So just for funsies, let's do it. We're going to make a u substitution. We're going to let u be the entire inside of that square root, which means that du is going to be 441 over 4 dy, or dy is going to be 4 du over 441. Now, when you do a u substitution, there's two ways to go from here, right? We can proceed as follows and then reverse the substitution back to the original y so that we can apply the limits of 0 and 3, or we can just forget y from this moment on and never have to go back to it. So I'm going to do that. If u is 1 plus 441y over 4, and remembering that the endpoints of 0 and 3 are values of y, we can say that y equals 0 is going to give us u equals 1. And y equals 3 is going to give us u equals 1 plus 441 times 3 over 4. Now, what value is that? $13.27 over 4, gross. However, once we put all that in place, now we have this arc length integral is the integral from 1 up to 1327 over 4 square root of u times 4 over 441 du. So this right here is the square root of u. dy is this stuff. And then we also changed the limits of integration. So I'm going to be flipping the page here. So I'm going to factor out that 4 over 441. We're doing the limit, the integral from 1 to, what the heck was that terrible number? 1327 over 4. Ugh. And then the square root of u, which is just u to the 1/2 du. And now we're ready to roll, right? So 4 over 441 times the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, which is times 2/3. And we're going to evaluate that from 1 to 1327 over 4. And altogether, 4 over, let's see, 4 times 2 over 441 times 3. There's no cancellation that's going to happen there. And then here we'll have 1327 over 4 to the 3/2 minus 1. 1 to the 3/2. Okay, this is pretty gruesome. I am cheating. I did this a little bit before. Oh boy, so we got an 8. And we got a 441 times 3. I'm not going to simplify that yet, and here's why. This interior, this 1327 to the 3/2 isn't going to get any better. However, 4 to the 3/2 is the square root of 4 cubed. 2 cubed. So we get that. And now, at least this 8 can be multiplied through with a cancellation there, and we'll turn that into an 8. So now I'm going to have, let's see if I can remember this, 1327 to the 3 halves minus 8. Back to the other page, times 1 over this number, which happens to be 1323. And if you don't like that fractional exponent, that 1327 to the 3 halves is 1327 times the square root of 1327. So that's what the arc length ought to be. Hoo boy. I'm going to save that quotient, that term out front for last. 1327 times the square root of 1327 minus, oops, get it outside the square root, minus 8 over 1323. Again, where did it go? There it is. 1327 square root of 1327 minus 8. That whole quantity divided by 1323. Check the answer. Green. Now, there's some red there because I'm not submitting answers. I'm just checking them in the administrator mode. But so don't ignore that red. Don't let that red make you mad. It's this green down here. Peace and tranquility from green in web work. Okay, here's one more. I promised 3, so I'm going to do this one too. Find the arc length. I'm going to write it down, then switch over to it, of 1/8 negative x squared plus 8 natural log of x on the interval from x equals 4 to x equals 6. And there's nothing different about this one other than it's got some slightly different functions in there. But here it is. There's my transcription of that problem. We're looking for the arc length here. I'm going to multiply through this coefficient of 1/8. Just so we can clean up that natural log term a little bit. All right, now remember, I'm not going to rewrite it, but we're doing integral square root of 1 plus the derivative of this squared. So I'm just going to build that interior of the integral, the integrand, from the ground up. Derivative. Well, take the derivative of that first term. It's negative 2x over 8 or minus x over 4. And then natural log of x, it has a derivative of 1 over x. You know what? Heck. Let's just go for it. I'm just going to build that. That's the square root of 1 plus negative x over 4 plus 1 over x squared. Like so. And so the arc length altogether is going to be the integral from 4 to 6. Ugh, that's awful. Let me erase that. Square root of 1 plus dy over dx closed my parentheses too soon, squared dx. Okay, now under normal circumstances, what I might have done is gone back here to this term and multiplied it out, see what it looks like, see if it's easy to add a 1 in there. Maybe when I square that, I get a negative 1 that cancels the plus 1, but that doesn't happen. But maybe you multiply this out and then get a common denominator among those terms and the plus 1, and then combine everything into one term, and then maybe the square root sign can simplify something. But I already know, remember I've looked ahead at these, that's going to get us nowhere. So any simplification that we do to this is not really going to present us with something that's solvable easily by hand. So I'm just leaving it like this. I'm going to go over here back to Maple. 4 to 6 square root of 1 plus negative x over 4 plus 1 over x squared. I mean, this is basically an immediate transcription of the arc length formula for this function with no significant simplification whatsoever. Now, the net result doesn't look awful, but try to do it by hand if you want a challenge. It's just gross. I'm going to use properties of logarithms to combine the two natural logs just to make it easier to type in when I flip back to WebWork. Natural log of 3 minus the natural log of 2 is the natural log of 3 divided by 2. So there's a slightly tidier version of that value. And so now, go back here, we've found the arc length should be 5 halves plus natural log of 3 halves. Check it. Peace and tranquility for all 3 arc length problems. Okay, so the story here is arc length integrals are nasty. Hopefully your instructor gives you the flexibility to use some tech to help get final answers, or just says construct the integral that would give you the arc length of this function from here to there and put it in a nice simplified form so that it's easy to check. That kind of answer. Okay. The big strategy that I'd recommend here is, again, because these integrals can get big and bloated, don't start, don't do this. Don't write down integral from 1 to 7 of square root of 1 plus dy dx squared dx, and then rewrite that whole thing once where you've only replaced dy dx, and then rewrite the whole thing again while you're simplifying the squared, and rewrite the whole thing again while you're simplifying the 1 plus. Just build it from the inside out. Get dy dx. Look at what dy dx squared looks like. Add 1 to it. Forget the integral. Just see what you're doing with that expression, because maybe it'll simplify a little bit. And then when you're happy with that result, then you come along and put on the integral sign and the square root and the dx. And that helps you focus on the little bits and pieces. If something goes wrong in this, it's generally going to be from the algebra that's going on underneath the square root. So get the clutter out of your way for a bit until it's time to put things in place for the integration. Oh, and I also mentioned I would say something about that trig identity that I used to turn 1 plus tangent squared into secant squared. Generally speaking, as long as you know this one, which at this point, you better know this one. If you're doing arc length integrals, by now you better know sine squared plus cosine squared is 1. If you know this one, you can confirm or check or derive a ton of other expressions. For example, that one integral problem we did in the first arc length, we came up with a 1 plus tangent squared. Oh, that looks familiar. Is it secant squared? Is it negative secant squared? Can we simplify that with a trig identity of its own? Well, one choice is to go open a book or get online and search, open a book, flip through pages, look in a big table and see if you can discover some identity that has to do with tangent squared. Or you can just write this one down and then say, by golly, I wish one of the terms in this function or in this identity was a tangent squared instead of a sine squared or a cosine squared, because then I might have something. And remember, who's in charge of this the moment we wrote it down? Remember, we are in charge of that the instant we wrote it down. If we would like to introduce a tangent squared into that identity, then damn it, we can introduce a tangent squared into that identity. But we only have sines and cosines to work with. Now, what's the definition of tangent? Sine squared over, or tangent is sine over cosine. So tangent squared would be sine squared over cosine squared. Oh, wouldn't it be great if this was a tangent squared instead of sine squared? Well, it would be great if we could take that term and divide it by cosine squared, because then it would turn into tangent squared, right? And remember, we're in charge. If we want to divide that left-hand side by cosine squared, then dang it, we're going to divide that left-hand side by cosine squared. Nobody can stop us. There aren't math police, right? So we're going to take this identity and we're going to divide this left-hand side by, well, do it Do it properly. I'm getting too excited here. Divide it by cosine squared. We are allowed to do anything we want to any equation, usually, as long as we do it to both sides. Okay? We're in charge. We are allowed to divide the left side by cosine squared as long as we do it to both sides. And now, remember, this cosine squared is dividing both the sine squared and this cosine squared. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And over here, 1 over cosine squared is secant squared x. And ta-da! We've now confirmed that identity. Okay, so when in doubt, start with sine squared plus cosine squared. Decide what operation you would like to do on that identity to turn one of the terms that are showing into something different you might like to see. Do that thing as long as you do it to both sides, and out pops a brand new identity. All right, 25 minutes was enough. Thanks for watching. I hope it helped.